chlorine bonded to another chlorine atom. What kind of bond would that be? That's going to be just nonpolar covalent, right? What about hydrogen bonded to bromine? And you can see the difference between those numbers there. Where am I pulling these numbers from? Where am I getting them from? The chart, right? The table, right? So go a couple slides back. Instant replay. This. So I'm just taking numbers off this chart, right? So bromine is 2.8. Hydrogen is 2.1. Okay, 2.8 minus 2.1 gives me 0.7, right? Okay, so that's going to be polar covalent because now it's 0.5. You know, it's above 0.4 in the difference there. Okay. This will probably ring familiar to you, hopefully. If I have hydrogen bonded to bromine, okay, and if I have 2.1 here and 2.8, okay, which way are the electrons going to want to go? Towards the bromine, right? So if I were to draw a bond dipole, you might remember this from Chem 107, but if I were to draw a bond dipole showing the partial charges of the ends of the molecule, this is what it would be. Right? The electrons are going to want to point towards the bromine because the bromine has a higher electronegativity. It wants electrons more. It's going to outcompete that hydrogen for electron density, if you will. Does this look familiar at all from Chem 107? Hopefully. Certainly my class. I don't know if anybody else looks familiar. Hopefully. I hope your professor showed you this. I really do. What about sodium and fluorine? That's ionic, right? You know, it's a 3.1. And it kind of makes sense too because going back to metal, non-metal for ion compounds, sodium and fluorine are metal and non-metal. What about potassium and iodine there? So here's the thing that drives me crazy. It's 1.7, it's below 2, so you would say polar covalent, right? But actually it's ionic. Because the rules for nomenclature override the numbers. Okay, and so this is why I kind of don't like using electronegativity difference to determine what kind of bond you have. So why am I introducing this? Because ultimately you're going to use just the concept of electronegativity to put together Lewis structures, and that's where we're going. Okay. So to classify bonds, I got to tell you right now, bond polarity, I don't care about it. I don't care about it. It's useless, okay? It's only useful to put together Lewis structures. That's all it's good for. Okay, so just understand, the numbers are just there to give you a context for where the electrons are going to go once we get to a molecule and say, well, is this molecule polar? Okay, you know, and that's really where this is going. Okay, so I'm just introducing bond polarity really to get us to molecular polarity, okay, which is where we're going. Okay, so a polar bond has a dipole moment, okay, but it's a bond dipole, it's not a molecular dipole. Okay, so a polar molecule has a net dipole, that's why they use the word net. A polar molecule has a net dipole moment as well, but we have to get through VSEPR first before we get to molecular polarity. But we will use electronegativity to do Lewis structures. So it's bond polarity, molecular polarity. I will be honing in on this in the next couple weeks. Okay, so it looks like we're going to have to kind of get to the tail end here. How about we just end right here, and then we'll do Lewis structures next time.